In section 8.4, we're going to look at what's called the definite integral. So first of all, I've started off with the definition of what a definite integral is. Suppose that you have a function f of x, and the function is continuous on a given interval a to b, including the values of a and b. And suppose that the indefinite integral, recall that the indefinite integral is given by this symbol right here, the integral sign followed by f of x dx. So suppose you find the indefinite integral of some function f of x, and we indicate that with the capital letter f of x plus c. So this capital F of x is the indefinite integral of the original function f of x. And of course, we always put plus c because of our constant of integration. The actual number, capital F at b minus capital F at a, is called the definite integral of the function f of x from a to b. So symbolically, I've indicated that right here. So when you see an integral sign, and the integral sign has numbers at the bottom and the top of it, that integral sign now indicates that you're finding the definite integral as opposed to the indefinite integral. And the way you calculate the definite integral is you take the antiderivative f and you substitute the value of b into it, and then you subtract the antiderivative f at the value of a. So your answer is going to be an actual number. It's not going to be a function. A definite integral is a number. The numbers a and b that you see on the integral sign, they are called the upper and lower bounds of integration. The bottom number obviously being the lower, and the top number being the upper. So now we'll have a look at a couple of examples of how to actually calculate the definite integral of a function over a given interval. In this example, we're being asked to evaluate the definite integral between 1 and 4 of the function 2x plus 3 with respect to x. So the first thing we have to do when we calculate any integral, whether it's definite or indefinite, is we need to find the value of the integral. So of course here we're just going to use our power rule. So we need to find the antiderivative of 2x. So we add 1 to the exponent, which would be 2 divided by 2, and we'll get x squared. And then the antiderivative of 3 would be 3x. And then we're being asked to, in this case, not find an indefinite integral. We're being asked to find the definite integral. So the way we indicate that is we find our antiderivative, and you'll notice I haven't put down the constant c. I'm going to address that in a second. When you're finding a definite integral, we don't need to put the value of c, and there's a reason for that. So what we want to do here is we want to evaluate x squared plus 3x between the bounds of integration of 1 and 4. So what we do is we just simply put a bracket behind it, and we indicate the 1 and 4. Now, if you recall from a moment ago that the actual formula for the definite integral is that we have to find the antiderivative f, which is this right here. This is f. We have to find that at 4 and subtract the antiderivative at 1. Now, I would recommend at this point that you do the calculation separately. If you actually try to plug this into this formula, it can get really confusing, especially with the minus sign and not including brackets. So I'm going to recommend that what you do is that you work out each one separately. So you start by finding the antiderivative f at the point 4. So that means you simply substitute the number 4 into your antiderivative. So that would be 4 squared plus 3 times 4, which will give us a value of 28. Then you calculate the antiderivative at the value of 1, which would be 1 squared plus 3 times 1, which is 4. And now we don't run into trouble with the negative sign. Our answer is just going to be f at 4 take away f at 1. So now we're just going to plug in f at 4, which is 28, subtract f at 1, which is 4, and our answer is 24. I want to stress that when you're finding a definite integral, your answer is always going to be a number. as opposed to an indefinite integral, in which case your answer will be a function. Now we're going to talk a little bit later on about the significance of that number 24, but all we want to do right now is practice finding definite integrals. Now a really good question at this point is, why didn't we have to put the constant c? So what about the constant of integration? C. I've stressed to you throughout the beginning of chapter 8 that when you're finding an integral, an indefinite integral, that it's important to put the constant c because we don't know whether the original function had a constant. If we were doing this question right here and just finding the indefinite integral of 2x plus 3 with respect to x, we would write x squared plus 3x plus c. Then if we tried to find the definite integral between 1 and 4, using our formula, we would calculate, so this would be the indefinite integral of 2x plus 3 dx, sorry, the definite integral. So the indefinite integral, there are no limits of integration. We're just finding the antiderivative. In a definite integral, we're substituting the value of 4 and the value of 1 into our antiderivative. Well, our antiderivative has a constant c, but look what happens when we plug the numbers in. So first of all, I'm going to plug 4 into my antiderivative, and I'm going to get 4 squared plus 3 times 4 plus c. And then I'm going to subtract what I get when I plug 1 into my antiderivative, which would be 1 squared plus 3 times 1 plus c. This bracket here is going to be 16 plus 12, which is 28 plus c. Subtract, this bracket ends up being 4 plus c. If you distribute the negative sign through the bracket, you get 28 plus c minus 4 minus c. And the reason why I did this for you is I wanted to draw your attention to what happens to the integration constant c. No matter what your limits of integration are, your boundaries, the constant c is always going to cancel. And you're just going to get the value that we got in this case of 24. So the point I want to make here is that when you're calculating a definite integral, you don't need to put the constant c, because what's going to happen is eventually it's just going to cancel out anyway. So it's not that the c is not there, it's just that it's not necessary in our calculations. But please, you want to always remember that when you're doing an indefinite integral, if you have no boundaries on your integral sign, make sure you always put the constant of integration c. It always belongs there. In a definite integral, you can ignore the c because it's simply going to cancel anyway, and it's just extra work that's not necessary. In our next example, we're being asked to find the definite integral between -3 and 0 of the reciprocal function 1 over x plus 2 with respect to x. The reason why I've selected this example is I want to draw your attention to the definition of a definite integral. If you recall, it said that the function had to be continuous over the interval that you're being asked to find the integral of. In this particular function, 1 over x plus 2, if you were to plug the number -2 into this function, you'd have a 0 in the denominator. You may recall that that's called an infinite discontinuity, and it would occur at the point x equals -2. And since the number -2 is inside the interval that we're being asked to find the integral of, we have to come to the conclusion that the definite integral cannot be evaluated. So for our final example, let's do a trig question. We're being asked to find the definite integral between 0 and pi of the function sine x dx. So the first thing we have to do is calculate the antiderivative. Well, we know that the antiderivatives of sine and cos are each other. So the antiderivative of sine, a good guess would be that it's cos. But if you recall, when you take the derivative of cos, it's negative sign. So we're going to have to compensate for that by putting a negative in front. So this would be the indefinite integral of sine x. And of course, there would be a constant c, but as I've already expressed, we can ignore it. Now we're being asked to find this integral between 0 and pi. So you can indicate that with a bracket, and then your limits of integration, 0 and pi. So first of all, we have to plug pi into our antiderivative. So if we plug f at pi, we would get negative cos pi. Now pi is 180 degrees. If you think back to your cos wave, a cos wave has a cycle that looks like that. At 180 degrees, the value of cos is -1. So this is going to be negative, -1, or just 1. We then calculate the antiderivative at 0, which would be negative cos 0. Cos at 0 has a value of +1. So this will end up being negative bracket 1 or -1. And the definite integral would be f at pi subtract f at 0, which would be 1 subtract -1, which would give us a value of 2. Now that brings to a close our study of definite integrals, but sort of as a lead into the next chapter, a good question might be, what have we actually found? Like what does that 2 represent? So let's say we drew a picture of this function. Let's say we drew a picture of a sine x. The graph of sine x would look something like this. A sine wave starts at 0 and travels up to 1 at 90 degrees, back down to 0 at 180. So a sine wave travels up like this, and then in quadrants 3 and 4, it just travels in the negative direction, so like this. So what does this number 2 represent? Well, we're being asked to find the definite integral of a sine wave between 0 and pi. So between 0 and pi would be this region right here. Well, it turns out, and we'll see why in chapter 9, that that number we just found is actually the area of this graph. It's the area of the graph under the sine wave and above the x-axis. So in this particular example, if these units were, like if they were just units, not any particular unit, we would say that the area of this graph would be 2 units squared. So definite integration is going to give us the ability to find areas bounded by curves that aren't linear. And that leads into what we're going to do in chapter 9.